Greetings and welcome to Chapter 5, Lesson 5.3, the Exponential Distribution. Get to know the new terminology for this lesson. Click on each of the words, learn its definition and meaning. When you are ready, click Continue. In the previous lesson, we dealt with uniform distribution, meaning that every event had the same likelihood of happening. But that's not always how things are. Many times we'll be in a situation where a lot of little things will happen and very few big things will happen. For example, earthquakes. We have a lot of little earthquakes in California. Most of them you can't even feel. But if you go look at the recent earthquake website, you'll see a lot of little earthquakes happening. And very few large earthquakes happen. Of course, the large earthquakes get our attention. We can also utilize this idea of a lot of little things and very few larger things when we're talking about, how long will it take before a call center receives its next phone call? How long of a piece of machinery will work without breaking down? And how long will time elapse before an earthquake occurs in a given region? So this distribution, this idea of a lot of littler things and very few large things, is in the exponential distribution curve. A lot of little things, very few big things. So you'll see the curve start very high and then taper off. This is the exponential distribution. You may have gotten the feeling that when working with distribution, we're really concerned with two things. One, the curve itself, and two, the area under the curve. The curve itself is the probability density function, that's f of x, and then all the probabilities under the curve will always add up to 1. Now with the exponential distribution, it's not just a straight line. If that was a line, then it would be kind of y equals mx plus b, or f of x equals mx plus b, the good old line function. But this is a curve, and so you can imagine our function is going to be a little bit more complex. In fact, the probability density function f of x looks like this. F of x equals lambda e to the negative lambda x, where lambda is 1 over our average mu, and our standard deviation and our average equal one another. So sigma equals mu. I do want to state a little point. In our textbook uses m for lambda. And m is not a standard character in this formula, and I want to use the standard formula using lambda because in the event that you do search using Google or your search engine that you like to use, I don't want you to get confused that you're not coming up with the same exact formula, because ours has an m and most everybody else, the standard is really using lambda. So I'm going to use lambda. I'm going to stick with the standard versus how our book does it. The second thing we are always concerned with distribution is the cumulative distribution function. That's how you get the area inside the shaded region. How do we get our probability? And that function is probability that x is less than some value, so our big X is less than little x, is 1 minus e to the negative lambda x. Now, x must be greater than 0. We're not going to be dealing with any negative numbers. Our curve starts at 0 and goes on to infinity. So we're never going to deal with negative numbers for our 0, or for our x value. It's always going to be greater than 0. Now, if our less than a particular value is 1 minus e to the negative lambda x, then our x is greater than a particular value is e to the negative lambda x.
And if we are looking for a range of values, the probability that A is less than X is less than B, then our formula is going to be e to the negative lambda A minus e to the negative lambda B.
Now, you might feel like this is more complex, and it is versus the uniform distribution, but let's work through an example. Let's let X be the amount of time in minutes a postal clerk spends with his or her customer. The time is known to have exponential distribution with the average amount of time equal to 4 minutes. First things first, we need to create our probability density function, f of x. Now, we know that our probability density function for an exponential distribution is lambda e minus lambda x. Lambda is just a number. Lambda is 1 over our average mu. Now we do need to roll back into the equation to look for what our average is, and it looks like our average amount of time is equal to 4 minutes. So mu equals 4, and therefore lambda equals 1 over 4, or 0.25. Let's use 0.25. Our f of x, wherever we see a lambda, we're going to put in this 0.25. So our f of x equals 0.25 e to the negative 0.25x. Okay, we have our probability density function f of x, and if we needed to graph what this function looks like, we do have the capability of doing that. I'm just going to use a generic graph for the exponential function. It just makes it a lot easier. But in terms of what would this look like, how would I add to this graph to make it more custom, is where it hits the 0 line would be 0.25. That's where it's hitting the 0 line. I can customize it like that. Now that we have our probability density function, we know what our graph looks like. Let's find the probability that x is less than 3. Because we're looking for a value x is less than 3, we're going to use the function 1 minus e to the negative lambda x. Now, in the back of my mind, I always have to kind of keep that thought that x always has to be greater than 0. And indeed, of course, 3 is greater than 0, so I'm good there. We know x is 3. We know our lambda is 0.25, so we're going to plug in these values. We can plug them directly into a calculator and see what the probability is. So 1 minus e to the negative 0.25 times 3. Plug that in, we get 0.5276. So the probability that x is less than 3 is about 52%, nearly 53%. Now, I do want to let you know that in previous distributions, when you put in the value of your average, your mu, you were expected to get 50%. So in this case, if I put in 4, our average is 4, and if I let my x be 4 or less than 4, you would expect 50% to come out. But the shape is not consistent. We have a lot of values being smaller versus larger. So your intuition might be if you put in the average value, 4, you should get the probability of 0.5. Don't expect that on the exponential distribution. Okay, I just want to give you the heads up. You're building your intuition about these distributions, and in the past, when you've put in the average, you kind of come up with 50% or 0.50. In the exponential distribution, that won't happen. That's not where 50% of your probability lies. It's going to be much smaller value than your average. This data is very skewed. Let's find the probability that x is greater than 6. Now, when we're dealing with greater than a value, we're only dealing with the function of e to the negative lambda x. We know what our lambda is. We know what our x is. We're going to plug these in and throw them into a calculator and get our probability. So the probability that our x is greater than 6 is going to be e to the negative lambda times x. So negative 0.25 times 6. And that equals 0.2231. So about 22% of the time, our value is going to be greater than 6. For a function that looks so complex, it's really quite straightforward to put it into the calculator. Let's now find the probability that x is between 4 and 5. So 4 is less than x is less than 5. Well, we know the probability of x being less than 5 is this full shaded region. And we're only looking for that area between 4 and 5. So it's going to be the probability that x is less than 5 minus the probability that x is less than 4. We've got to get rid of everything below 4 because we only want it between 4 and 5. The probability that x is less than 5 is going to be 1 minus e to the negative 0.25 times 5 minus our probability that x is less than 4, which is 1 minus e to the negative 0.25 times 4. Now we need to distribute that negative through, and we'll get negative 1 plus e to the negative 0.25 times 4. The 1 minus 1 will drop out, and we have negative e to the negative 0.25 times 5 plus e to the negative 0.25 times 4. But just reordering that, you get the e to the negative 0.25 times 4 minus e to the negative 0.25 times 5. Now, the reason why I worked all of that out, and from there on, it's just a calculator problem. You throw it in the calculator, and you get 0.0814. But the reason why I worked out all those steps, so you could see it, is in short, if you have the probability that some value is less than x is less than some other value, you can immediately jump to that last step before throwing it into a calculator, that it's going to be e to the negative lambda first value minus e to the negative lambda times the second value. So again, if you have a range going from a low value to a high value, then it's going to be e to the negative lambda times low value minus e to the negative lambda times the high value. So you can immediately jump to that step. Now I am going to show you how to do a problem using the TI-84 Plus, but I do want to say any scientific calculator that has E, you'll be able to use. I'm showing it using the TI-84 Plus, but you'll be able to use it with any scientific calculator. So here's our problem we're going to pose. On average, a certain computer part lasts 10 years. The length of time the computer part lasts is exponentially distributed. We want to know what's the probability a computer part lasts more than 7 years. On average, how long would 5 computer parts last if they were used one after another? 80% of computer parts last at most how long? And what's the probability that a computer part lasts between 9 and 11 years? So that's what we're going to be working out on the TI-84 Plus. In other distributions, we were able to use one of the built-in functions. So we would go to second, vars, and we'd find our distribution here, and we worked with binomial, Poisson, geometric. With exponential, we don't have a built-in function like this, but that's okay. The math is relatively simple in terms of what we need to do on the calculator to be able to figure it out. So here's what we are going to need to use. We are going to need the e to the x button. which is second ln. So it's right here in blue. That is our e to the x button. And if you're curious, e is an actual value. It is a number like pi. If you're curious as to what it is, you can go e to the x and then the exponent to be 1 and hit enter, and you'll see that it's approximately 2.7183. Now, e goes on forever. This is just 4 of the decimal places for e. The other key that we're going to need, besides normal math stuff, is the ln key. So instead of hitting second ln, we'll also need the ln. We will use e to the x when we are looking for probability. When we are given the probability, we will need the ln key. Ln and e to the x are opposite functions of one another. Just like addition and subtraction are opposites of one another, multiplication and division are opposites of one another, these two functions are opposite of one another, e to the x and ln. So again, when we're looking for probability, I'll use the e to the x. When I am given probability and I need to find my x value, then I will use the ln key. Let's move on to an example of how we can use the TI-84 Plus to solve some exponential distribution problems. Let's say on average, a certain computer part lasts 10 years. The length of time the computer part lasts is exponentially distributed. So we're going to need some information to work with the exponential distribution function. 1, I'm going to need to know my x value. And 2, I'm going to have to know my lambda value. My lambda value is 1 over my average. In this situation, my average is 10 years. On average, a certain computer part lasts 10 years, so my average is 10 years. Lambda, therefore, is 1 over 10, in other words, 1/10. Now that we know our lambda, we can move on to working with problems. What is the probability that a computer part lasts more than 7 years? When we're working with more than 7 years, the equation we're going to use is e to the negative lambda x power. Because this is more than 7 years, my x value is 7, my lambda is 1/10, and therefore I can just start keying it in. Second, e to the x, parentheses, because this is all goes up into my exponent. It is a negative lambda, so I want to use the negative key, not the subtract. Negative 1/10 times my x value of 7, end parenthesis, and I hit enter. And the probability that my computer part will last more than 7 years is 0.4966. Let's find the probability that it will last less than 3 years. Well, when we work with less than a value in exponential, I need to first start off with 1 minus, and now I use my exponential function. Second, e to the x, my lambda has not changed, so negative 0.1 times the amount of my x, which is 3 this time. So the probability that the computer part will last less than 3 years is 0.2592. It's about 25% of the time the part won't last past 3 years. What if we have the probability between a couple of times, like what's the probability that your computer part will last between 9 and 11 years? Well, when we're in a particular region from 9 to 11, then here's what we can do. We can take the exponential function 1 minus our exponential function of the higher one minus 1 minus the probability or our lower boundary. But that's really big and lengthy, and it turns out that if you just do your exponential function of your lower one minus your upper one, you'll get the same answer. So if it is in between, I am just going to go second e to the x, my negative lambda, times my lower boundary. Okay. And then I want to subtract it from the upper boundary. So I did hit the key, the over key to get out of the exponent. I don't know if you saw me do that, but I did. Exponent second, e to the x. My exponent is negative lambda times my upper boundary of 11. You'll see my little cursor is still up there in the exponent. If I want out of the exponent, I could just hit over and it gets out of that exponent. Okay. If you were in between two values, exponential function to the lower boundary minus exponential function to the higher boundary. So the probability that my part will last between 9 and 11 years is about 0.0737. What if I am told what percent or probability? 80% of the computer parts last how long? 80% of computer parts last at most how long? Well, this time I'm given the probability and I have to work backwards to find this x value. That means I have to use the ln. And the equation that I'm going to use is the ln of 1 minus the probability that I'm given, 80% in this case, so 0.80, divided by my negative lambda. And therefore, 16.0944, in other words, 80% of the parts will last at most about 16 years, 16.1 years. Okay, so just to recap, if you are looking for probability of a value greater than or more than, you will just use the exponential function of e to the negative lambda x. If you are looking for a value at most or less than a particular time frame, then you're going to have to use 1 minus the exponential function e to the negative lambda x. And when we have a range of values from a low value a to the high value b, probability that a is less than x is less than b, then we'll have e to the negative lambda a minus e to the negative lambda b. If you are given your probability, then what you'll do is you're going to use the formula of the ln of 1 minus your probability, all divided by. You've reached the end of this lesson.